Okay, welcome to Ionic Compounds Introduction. I'm Mr. Schmidt. We have just a few things that we have to go over today, and I have our objectives listed here in the slideshow, and they are to determine the number of valence electrons in an atom of a representative element, to determine the number of valence electrons, I guess I wrote this thing twice, and to describe how cations are formed, explain how anions are formed, and then also we're going to draw some electron dot structures. So in order to show like the number of valence electrons in the atom. So let's get started on that. All right, so determining the number of valence electrons in an atom of a representative element. I'm going over some of these things because some students were in Mr. Malden's class and maybe they missed these objectives. So we're going to cover this in a little more detail than some other students may need. But if you look at our representative elements are simply these groups, 1A, 2A, 3A, 4A, 5A, 6A, 7A. Those are our representative elements. And then another very important one is our noble gases. All right. But we're looking at how to determine the number of valence electrons in the atom of a representative element. So we're going to stick right to these 7 groups, group 1A through 7A. And so that's very important to know what representative elements are in doing that. Okay, so how do we determine the number of valence electrons? Well, you might start with, what is a valence electron? Valence electrons are the electrons in the highest energy level. All right, electrons in the highest energy level. So what we should, whoa, my goodness, I changed slides here. What we should see is if we just pick an atom, and let's choose lithium from one of our groups, and you might notice that lithium is in group 1. All right, it's in group 1. Lithium is in group 1. If we write the electron configuration for lithium, and I do have a video for how to write electron configuration posted from last semester, you may look at that. But we have, it's in energy level 2, so it's in 2, and it's in S, and it's in 1. And so we have 1s2, 2s1. You might notice lithium has 3 protons, so it's going to have 3 electrons in order to be a neutral atom. All right, and so we count our electrons. We have 2, and we have 1. Whoops, 1. So 2 plus 1 is 3. So that's where we're getting these 3 electrons from. And the number of protons and electrons should be equal if you have an atom, or an atom has a neutral charge. There's no charge indicated here, so that means that is neutral lithium. It means it's a lithium atom. And so what we're interested, though, in is knowing the number of electrons in the highest energy level. If you look at our energy levels, we have 2 of them here. We have energy level 1, and we have energy level 2. And energy level 2 is the highest energy level. So how many electrons do we have in that highest energy level? There's only 1. You can see it right there. So lithium has 1 valence electron. And what you should also notice is 1 valence electron, and it's in group 1. So if we did the same thing with sodium, all right, we'd have 1s2, 2s2, 2p6, 3s1. And once again, we're just interested in knowing the number of valence electrons, or the electrons in the highest energy level. The highest energy level is 3. How many electrons do we have there? And that is 1. All right, so sodium, lithium has 1 valence electron. Sodium has 1 valence electron, and they're both in group 1. And so what this is saying, on our notes, it says atoms in the same column have the same outer electron configuration, and they have the same valence electrons, or the same number of valence electrons. So group 1 is all going to have one valence electron. All right, they have the same outer electron configuration. What they mean by that is in the highest energy level, they have the same number of electrons. Whether we're looking at lithium, it has one electron in its highest energy level, and so does sodium. And what you notice about those is that they are both in the same group. So we looked at potassium, it has one valence electron. Rubidium, cesium, francium, all of those have one valence electron. And it's very nice because the number of valence electrons matches the group number. You see, we're in group 1, there's one valence electron. If you have an atom in group 2, it should have 2 valence electrons. In group 3, 3 valence electrons, 4 valence electrons. Group 5 is 5 valence electrons, 6 valence electrons, 7 valence electrons. And so there you go. That's how you know. Now, it's also very important to note. All right. So you should be able to, well, I'm going to go back on my, it's important to note, but you should be able to recognize the number of valence electrons by looking at the groups of your representative elements. And the only ones we're really going to be asking you about are your representative elements, those groups 1A, 2A, 3A, 4A, 5A, 6A, 7A. And then maybe the noble gases, which follows the same trend. It's in group 8A and they have 8 valence electrons. So you can tell the number of valence electrons just by looking at the group number, and it matches every time. Okay, so another thing that's very important to note, and I was going to get to this a second ago, is that you have to be able to determine your metals from your non-metals because they behave differently. All right, so everything over on this side of the periodic table all of these right here are going to be considered, let me see if I can get something a little darker. Well, you can see over that, metals. All right, these are all going to be metals. All right, they're all metals, this whole side here. Now, the side that I'm about to highlight, it's a little easier to see, side over here, all of these are going to be non-metal. And I think we have to add hydrogen to that. I didn't do that. I should have left it out of the metals, but that's hydrogen is a non-metal. All right. And so you need to make sure you understand the difference between metals and non-metals as well, all right? Because they behave differently. So that's where those are located on your periodic table. Okay, so now we want to write the electron dot structure, and it's a way of keeping up with valence electrons. So we have to know how many valence electrons we have in order to write a proper dot structure. So how do you write them? So you write the symbol, and so they're using just any X as a variable to represent any symbol. And so I'll do the same thing. And when you write these dots right here, they represent only valence electrons, only the electrons in the highest energy level. They don't represent all the electrons, but only those in the highest energy level. And you should have no more than 8 electrons in your highest energy level. It doesn't happen where you get more than 8. So the octet rule, in forming compounds, atoms tend to achieve a noble gas configuration, or they have 8 in their outer level, and they consider that to be stable. And there's an exception, except for the helium. Okay, I got interrupted for a second. I don't know where it was, but here we go back. So except for helium, it has only 2 electrons. It won't have 8. So we're gonna bring out that point a little bit. So if we have element X, and it doesn't matter how many valence electrons this has, because this is just representing any. The picture here shows 8, but it is important how you draw them, so that when you do have something that has less than 8 valence electrons, you can know how to draw this properly. So let's follow the rules here. It says you write the symbol, it represents the nucleus and the inner electrons, so the core electrons, and that means these dots represent only the valence. And they don't pair up until they have to. So I was going to draw this element X with the 8 electrons. I would draw them this way: 1, 2, 3, 4. You see how I put 1 on each side of the symbol, and then now they are forced to pair: 5, 6, 7, 8. And so that's how you draw them, and that's what that slide is telling us right there. Okay, so let's do a real element now. Let's try calcium. All right, so if we look at calcium, we have to first know how many valence electrons it has, right? How many valence electrons? So we go to our periodic table because it's the only thing we know, and we find calcium. Calcium is right here. And how are we going to know how many valence electrons it has? That's right, we look at the group, all right? It's in group 2, so it must have 2 valence electrons. So we're going to draw 2 valence electrons around our symbol for calcium, because remember, these dots represent only valence electrons. Calcium has way more than 2 electrons, but it only has 2 in its highest energy level. And so you can look at your periodic table and look at group 2. You can also write the electron configuration for that and see that as well: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. If you count all these electrons, you'll see there are a total of 20. All right, if you count all these little superscripted numbers, you would get 20 if you added them up. But in the highest energy level 4, there's only 2. And so we know there are 2 valence electrons. So we're only going to represent valence electrons here. So for calcium, we are going to put 1 dot on one side and 1 there. It does not matter whether you start top, bottom, left, right. I just will always start them with the top. So, but what you cannot do is you cannot do this. They cannot pair until they're forced to do this. So this would be incorrect. And this is correct. All right, then let's do that for another atom. Let's do that for maybe sulfur. If we have sulfur, how many valence electrons does sulfur have? Go to our periodic table. You always have to use your periodic table. There's no going around it. You find sulfur right here, and it's in group 6. So how many valence electrons will it have? Yeah, you guessed it, 6. So we're going to have to draw 6 dots representing valence electrons. So let's do that. Start 1, 2, 3, 4. Now they're forced to pair, 5, and 6. And so that is the dot structure for sulfur. And so all it really is looking at the number of valence electrons and then putting the dots to represent those valence electrons around the symbol. You have to do that in a very specific way. Okay. Now you may be getting a worksheet that looks something similar to this, and I have 2 of those in here. So lithium, I want you to first identify this as whether it is a metal or a non-metal. All right, so is it a metal? It is. And metals, you need to know for this section, they lose electrons. And when they lose electrons, they form, what I'm doing here, they form a cation, or they form a positive charge ion. Cation equals positive. All right. So you have to be able to write the electron configuration for this, this activity here. So the electron configuration for lithium, go to our periodic table, you can see that it's in energy level 2. There's 1, 2. It's in energy level 2, and it's in S1. So it's in 2s1. It ends there. So we can write 2s1, and we'll write everything before that, 1s2, 2s1. If you look at your periodic table, you should see that it has 3 protons, or an atomic number of 3. It's 3 electrons. And if you have the same number of protons and electrons, you will have a charge of 0, or what we say is a neutral charge. All right. And you can draw your Bohr model here. In your Bohr model, you're going to represent 3 protons, means that's lithium. Lithium is identified by having 3 protons. I could write Li, or I can write the 3 protons, and I'm going to write the 3 protons. And you can see that it has 2 energy levels, 1, 2. I like to label those. And then we just draw those electrons according to our electron configuration. So we have the 2 energy levels, 1 and 2. And so we just simply draw these in, 1, 2, and then there's that 1 valence electron in the highest energy level. And so you can see also lithium is in group 1, right? You saw that. So in group 1, you should see that it has 1 valence electron. So when we do our electron dot, what you're looking at there is lithium with a single dot. And that's all there is to that. Okay, so we're going to go and make the octet, though. All right. Lithium is going to lose an electron to make the octet. All right. And there's something funky going on with my computer. Don't know what. So when we make the octet, it's going to lose an electron so that it gets a noble gas configuration. All right. And so what that's going to look like is 1s2 for lithium. Now look where lithium is. Lithium is right here on the periodic table. And so if it loses 1 electron, it's going to look like helium. Well, how many electrons would helium have in its valence shell? Well, it looks like it would be 8, because it's in group 8A. It's the only one that's different, all right? Because it has a noble gas configuration with only 2, because it has that S orbital can only hold 2 electrons. It's a weird one. And it's also stated right here. You remember, each noble gas except helium, which has 2. So it does have a noble gas configuration because it looks like helium. All right, so 1s2. How many protons does lithium have? Well, that never changes. It says 3 plus. How many electrons now? If you count your electron configuration, it has 2 electrons. And if you have 1 more proton, this looks like this, plus, plus, plus. And if you have minus, minus, well, then these are going to cancel, and you're going to left with just a plus. So you have a 1 plus charge. All right. And so what does that look like in a Bohr model? It's very similar to what we had before, except for we lost a whole energy level. And now, instead of showing that second energy level with that 1 valence electron, we have just the 1 energy level with 2 electrons, which is identical to the configuration of helium, which is a noble gas. And the only difference now is we have 3 protons and 2 electrons. You must show that there's a 1 plus charge. All right. Now, when you draw an ion for a dot structure, you're showing that electron has been removed. And so you leave that out. There's no dots, but you do have to show the charge. All right. So you do show the charge. So it's going to be lithium 1 plus. And why is it 1 plus? Because it lost only 1 electron. If it loses 2 electrons, it will be 2 plus. If it loses 3 electrons, then it will be 3 plus. So on and so forth. Okay, now we go to another one. It's a little bit different. Nitrogen. You need to make sure you label these. This is a non-metal. And what do non-metals do? They gain electrons to get that noble gas configuration, and they form an anion, or a negative charge ion. So if we look at nitrogen, we see that it is in energy level 2, right here. All right, energy level 2, it has 7 protons. And we write the electron configuration for that is 1s2, 2s2, 2p3. All right. 7 protons. And you can, if you count your electrons, 2 plus 2 plus 3, that is 7. So you're showing that you have the same number of protons and electrons, and your charge is 0 or neutral. So if you draw your Bohr diagram for this, you're going to draw two energy levels. So this is identified by the number of protons, energy level 1, energy level 2. And so you draw 2 electrons in the energy level 1, and then 2 plus 3 in energy level 2. 1, 2, 3, 4, 5. And it has 5 valence electrons. You will notice if you go back up to your periodic table that it is in group 5. Isn't that interesting? So it always matches. All right. And then our dot structure, we know that it has 5 valence electrons. So we're going to write the symbol for nitrogen, which is N. And we're going to draw 5 valence electrons. 1, 2, 3, 4. And now they're forced to pair 5. And that's the perfect dot structure for a nitrogen as an atom. But once it reaches an octet, all right, it becomes an ion, and in particular, an anion or a negative ion. And so it has to have a noble gas configuration. Well, it gets to a noble gas configuration by gaining electrons. You see over here, it was 1s2, 2s2, 2p3, which is 5 electrons. So we have to make sure that is 8 electrons. So that's going to be its noble gas configuration. It gains, it goes from 3 to 6 to get to 8. All right. So the number of protons never changes because it's nitrogen. But the electrons did change. It went from 7 to 10 electrons. So now you have 3 more electrons than you do protons. So you have 3 of something negative. So it's going to make your 3 more of something negative. So your charge is going to be 3 negative. And so in this case, we're not eliminating an energy level, 1, 2. We are just simply adding electrons to our highest energy level, 3, 4, 5, 6, 7, 8, so that it has the octet or what is called a noble gas configuration. And so you look at your dot structure now, you will do the same thing, 1, 2, 3, 4, 5. But now you're adding 3 electrons because this is going to be negatively charged, right? It's a -3 charge. So you're adding 3. So just to show you that they're added, I'm just going to put a different color here. 1, 2, 3, but that's 8 electrons now. So for anions, when we have a negative charge ion, we put a bracket and then put the charge there, 3 minus. Whoops, there we go. And so that should help you out in being able to write the electron configuration or the dot structures, knowing how to determine the number of valence electrons, and seeing the electron dot structure will help us in the future when we want to make compounds, which is our next step. But for now, you should be well served. Thank you for watching.